Okay, I think we can start, and after other people are gonna join. So let's start.
Okay, welcome everyone, and thank you for tuning in to learn about the James Webb Space Telescope. Traveling back in time is the stuff of science fiction, but looking back in time is something that we can actually do. And it's primarily what we do with space telescopes. Looking back in time is made possible by the finite speed of light. If you look at a person seated next to you in the room you're in right now, you're not seeing them as they are. You're seeing them as they were a few nanoseconds ago. Why? Because that's how long it takes light to travel 1 meter from that person to your eyes. Now, a nanometer is a really, really small amount of time. So that transmission delay is completely imperceptible to us. But as we look at objects that are farther away, the effect becomes more pronounced. For example, if we had a magic switch that could turn off the sun and we flip that switch, it would be 500 seconds before we saw anything happen. Why? Because it takes light 500 seconds to travel from the sun to the earth. So when we look at the sun, we're not seeing it as it is, we're seeing it as it was 500 seconds ago. When we look at the nearest star, we see it as it was 4 years ago. The center of our galaxy, we see it as it was 25,000 years ago, and so forth and so on. So we use telescopes to look back in time to explore the formation and evolution of the universe. Now, the Webb telescope was conceived in the early 1990s to connect the dots, if you will, between these two famous images. Up at the upper left is an image of the oldest light in the universe, recorded by NASA's COBE satellite. This shows us what the universe looked like the moment it became transparent a few 100,000 years after the Big Bang. These pink and blue blobs in the image are temperature inhomogeneities that are the seeds from which galaxies will eventually form as the universe evolves, as shown in this cartoon. Around the same time as this COBE satellite flew, the Hubble Space Telescope was launched, and it took its deepest image that it could take right after launch. So it looked as far back in time as it could, and it took this famous image known as the Hubble Deep Field, which shows us what the universe looked like about 1 billion years after the Big Bang. And between this epoch seen by the COBE satellite and the epoch observed by the Hubble Space Telescope is a mysterious, poorly studied epoch known as the cosmic dark zone. And this cosmic dark zone is of tremendous scientific interest because it is the point in the evolution of the universe that the first stars and galaxies formed. Why is it poorly studied? Because we haven't had the right type of telescope in space to study it. And that was the original impetus for the Webb Space Telescope mission. Now, you've all heard the statement that space is expanding. What do we mean by that? Space is expanding. What you see on the screen now is an analogy that tries to explain that. Here you have a loaf of raisin bread dough that's been set out to rise. Now imagine that you are seated on one of the raisins. What would you see? You would see all the other raisins moving away from you, even though you are not at the center of the expansion. And no matter what raisin you chose to sit on, you would see exactly the same thing. This is a good analogy for what we mean by space is expanding. We don't mean that the galaxies, the raisins, are flying through space as if it was the result of some sort of explosion, but rather the space between the galaxies itself is actually expanding. Yep, I'm having a problem advancing my slide here, and I don't know why. And someone is drawing on my screen. Hang on for a second. Okay, so what does this have to do with the James Webb Space Telescope? When we look at those primeval galaxies, the first galaxies to form after the Big Bang, they emit their light in the ultraviolet part of the spectrum. However, as that light travels to us through the expanding space, through the expanding raisin bread dough, its wavelength is shifted from the very short wavelength ultraviolet to the long wavelength infrared. And so to see that light today, we have to build an infrared telescope. And the infrared capability that we put into the Webb telescope to see the first galaxies enables lots and lots of other science. Okay, so everything we know about the universe outside our solar system, and most of what we know about the solar system, all of that information comes to us encoded in starlight. And so as astronomers, we want all that information. And so we need all the starlight in order to extract all the information. But all the starlight does not reach the surface of the Earth. Our eyes have evolved to match a narrow, transparent window in the Earth's atmosphere, such that our eyes are sensitive to the familiar colors of the rainbow that you have all seen. And it's called the visible part of the spectrum. But there's a lot more light that impinges on the Earth. Most of it does not reach the surface of the Earth, which is good for us because some of it's harmful. Shortward of the violet part of the spectrum is the ultraviolet. Our eyes cannot see ultraviolet light, but our skin can be burned by it if you stay at the beach too long. Longward of the red part of the visible spectrum lies the infrared. Our eyes can't see infrared light, but your skin can sense it. If you hold your hand near a warm stove burner or a warm radiator and you feel the heat on your hand, what's happening there is your skin is sensing the infrared light emitted by the warm object. The Hubble Space Telescope was designed to operate in the visible and ultraviolet part of the spectrum. In contrast to that, the Webb telescope is designed to operate in the infrared and mid-infrared spectrum, in part to see those first galaxies. So infrared light is heat radiation, and the Webb telescope is optimized to see that light. Now, the spaces between the stars in our galaxy, the so-called interstellar space, is not a cold, empty vacuum. It's filled with giant clouds of molecular gas, dust, atoms, molecules, ions, lots of stuff. Here you have a picture of a giant molecular cloud complex in space called the Eagle Nebula. Young stars have been born here and are producing a lot of ultraviolet radiation, which is impinging upon this molecular cloud. This cloud consists of molecular hydrogen. And when the ultraviolet light impinges on this molecular hydrogen, it causes it to glow and produce this visible nebulosity, as we call it. Early in the Hubble Space Telescope's mission, it took a very famous picture of part of this Eagle Nebula called Pillars of Creation. And what you see here are these big filaments of molecular gas. And they're opaque because mixed in with the molecular hydrogen is lots and lots of dust that makes the filaments opaque. And inside those filaments, new stars are being born, but we can't really see the action because of the opacity. When we look at that same object, the same field with the Webb Space Telescope, its longer wavelength infrared capability allows us to peer through the dust and to see the star formation action inside. And so this is just one example of how the Webb telescope uses its infrared capability to study star formation close to home. Here's another example of a different molecular cloud. And here, young stars have been born, and their ultraviolet light is impinging on this cloud. You can see hydrogen streaming off into space. There's star formation occurring embedded in the cloud that we can in part see. One can see these columnar features similar to the pillars of creation forming with Webb's infrared capability that allows us to see through dust with great detail. We're getting lots and lots of new information and new insights into how stars form in our galaxy and others. Now, we know the basics of star formation. These giant molecular clouds in space collapse onto themselves due to self-gravity. And when those clouds collapse onto themselves, the pressure inside the cloud goes up. And when the pressure goes up, the temperature goes up. It's much like when you fill your bicycle tire at the gas station. The tire gets a little bit warm when it's fully compressed. Well, in the cores of these clouds, the temperature gets really, really, really warm to the point where nuclear fusion starts, and then the star is born. And when that happens, the new star is typically surrounded by a disk of material called a circumstellar disk that you can think of as material left over from the star formation. And these circumstellar disks are of tremendous scientific interest because they are the birthplaces of planetary systems like our own. When planets form in these disks and orbit their star, the planets sweep up material from the disk to cause it to take on this sculpted appearance that you see in this computer simulation that's running here. These are radio telescope imagery of actual sculpted circumstellar disks. And so one can see with this type of imagery, we can actually infer the presence of planets, exoplanets, orbiting stars other than our own, without actually having to see the planets themselves. And the Webb telescope is doing a lot of this work. Here are some examples. This is the circumstellar disk around the star Fomalhaut. And here is the Hubble Space Telescope image of Fomalhaut. And one can see that with the Webb telescope, with its ability to see fine detail in the infrared, we can see much more structure in this circumstellar disk to help us understand how planets are forming there. Here's another example where we're seeing the circumstellar disk edge on. This little black line here is that disk seen edge on. We can see these giant outflow jets emitting from the poles. And here's another example on the cover of Nature magazine. And with observations like this, we're able to better understand how stars form, and we can understand the chemistry and dynamics of what we're looking at here. Here is yet another example. This one is the closest star formation region to the Earth. It's about 400 light years away. And there are about 50 sun-like stars having just been born in this object. Here's one that has hollowed out a giant cavity in its birth cloud. This red material is a hydrocarbon and other molecular emission. All right, what we have here on the upper left is an artist's rendition of that debris disk surrounding our star, the sun, along with an actual map of where this debris lies. These chunks are chunks of rock and ice that are literally left over from the formation of our solar system. They are called the trans-Newtonian objects or Kuiper belt objects, and they are orbiting the sun in the outer solar system. We put special non-sidereal tracking capability into the Webb telescope to allow it to observe these objects and the outer planets of our solar system. We recently got our very first photograph of a Kuiper belt object back in 2014. NASA had launched a mission called the New Horizons mission, whose mission was to fly by Pluto. And when it finished the Pluto flyby part of its mission, we sent it on to this Kuiper belt object to take the very first image ever. And this is what we found. We found that it was two objects fused together. And this has since been computer modeled as resulting from a very low velocity collision between these objects that show that under those circumstances, they can fuse together without either one being destroyed. And this is of great interest to theories of planet formation, in which planets form by successive agglomeration of small particles into bigger ones to eventually produce a planet over 10 to the 8 years or so. And the Webb will be studying this process in great detail. Now, most of the liquid water in our solar system may not be on the Earth at all. Moons of Jupiter and Saturn, Europa and Enceladus, among others, are known to have vast oceans covered by a thick crust of ice. And when tidal forces act on this crust of ice, it cracks and leads to a geyser-like phenomena shown in this drawing, in which ejecta from this ocean is expelled out into space. And here is an actual photograph of that process happening, recorded by the Cassini spacecraft on a moon of Saturn called Enceladus. This is of great interest for the search for life, because we know from studies of the mid-Atlantic ridge on the bottom of the Atlantic Ocean here on the Earth, that there is life there that exists completely disconnected from the sun, thriving on chemical energy from volcanic vents. And the same thing could be happening on these moons of Enceladus and on Enceladus and Europa. Now, the Webb telescope has observed this ejecta. We have found that it is, in fact, water. We've taken spectra of the ejecta to measure its chemical composition in water. Big ring system and faint moons that were too faint for flyby spacecraft to see. Here is Jupiter's great red spot. Today, this is a storm that has been raging on the surface of Jupiter for 400 years or so. Today, we see that it's shrinking. The Webb observations may help us understand why it's shrinking, and the Webb may help us understand why the red spot is red. We still don't know the answer to that. Here we see the rings of Uranus like we have never seen them before. These rings consist of particles and chunks of ice and rock, and the Webb telescope, with its infrared capability, is exquisitely sensitive to ice and rock. So we're able to see this ring system clearly for the first time. Now, when I was a graduate student, there were no planets known outside our solar system. Today, we've identified more than 5,000, with the implication that there are tens of billions of habitable worlds in our galaxy. We don't know that they're inhabited, but we know they're there, and we know that they're habitable. And so the search for life is on like never before. The search for life is no longer the stuff of science fiction. It is very much a major science objective, uh, playing a key role in the beginning of this program. How can we search for life on an exoplanet that is so tiny and far away we could barely see the exoplanet? We use a process called spectroscopy, in which we use special optics to spread light out into its component colors so that we can see emission and absorption of individual atoms and molecules in the gas. Bumps and wiggles is due to atom and molecule is producing all of the bumps and wiggles. So we will be searching for chemistry in these exoplanet atmospheres that is indicative of life. How do we do it? We're using a process called transit spectroscopy. One can imagine some is doing lots and lots on exoplanets that are somewhat larger than the Earth, a few times the size of the Earth. If we're looking for extraterrestrial life, why do we care about water? It's not because alien life might get thirsty and need something to drink, but rather, in order for the organic chemistry of life to occur on a planetary scale, one needs to have a liquid solvent available on a planetary scale, and water is what we're most familiar with. So let's look at some results. Here are some Webb spectra of exoplanets. And the first thing you see here is it's not a flat line. There are lots of bumps and wiggles. These are planets that have atmospheres, and we're able to identify lots of chemistry in these atmospheres: potassium, water, carbon monoxide, sulfur dioxide, which is very interesting because that one is produced by photochemistry in the planet's atmosphere. So this work is just getting underway, but the Webb is searching many, many exoplanet atmospheres for signs of life using spectroscopy. Here is another example where we have discovered methane and carbon dioxide and possibly even dimethyl sulfide. So stay tuned for these results, and but it's very, very exciting, and we're getting information that we've never been able to get before. So when we first put pencil to paper or marker to whiteboard on what kind of telescope we had to build to do that sort of science, we realized that we needed 7 times the light gathering capacity of Hubble Space Telescope. And we needed Hubble's ability to see fine detail resolution. And that also requires producing a big mirror. And as I mentioned, we need a telescope that can work from the optical to the mid-infrared spectrum. So when we realized those 3 things, we realized that we had 2 enormous problems that almost stopped the project dead in its tracks. To get 7 times the light gathering capacity of the Hubble Space Telescope, we needed a primary mirror that is bigger in diameter than the biggest rocket. And to achieve a telescope that can work in the mid-infrared spectrum, we have to make the telescope very, very cold. Why? Because everything above absolute zero emits infrared light. So if you had infrared goggles on right now, you would see your body glowing in the infrared. The walls and floor of the room that you're in would be glowing in the infrared. If we didn't make the Webb telescope very, very cold, it would be blinded by its own infrared emission. How cold do we have to make it? Really, really cold, about minus 230 degrees Celsius. And so that was a huge problem because then and now there is no mechanical refrigerator powerful enough to cool something as big as the Webb to such a low temperature. So those were our 2 problems. Let's take a look at how we solved them. And let's talk about that thermal problem first. We didn't put the Webb telescope in orbit about the Earth the way most satellites are. We sent it to a special spot in space called the second Lagrange point of the Sun-Earth system. That's a mouthful. We just call it the L2 point for short. And this point is about 1 million miles away from the Earth in the anti-sun direction. Now, how does that help us cool the Webb telescope? Well, as the Earth orbits the sun, this pattern of Lagrange points, of course, orbits with it. And so one can see that an object placed at the L2 point, that object will always see the sources of heat on it as lying in the same direction. So the sources of heat are the sun, the earth, and the moon. And if the object is here, as the earth travels around the sun, it will always see those sources as lying in this direction. And so then we realized that if we just deployed a giant sun shield to block the light from the sun, the earth, and the moon, so that the telescope would always live in the shadow of that sun shield, it would cool passively by just radiating its energy away to the cold darkness of space. And so that's what we did. We designed the sun shield to be big enough so that we could point the Webb telescope 5 degrees toward the sun and 45 degrees away from the sun, and we're still in the shadow. And now, so that's an arc on the sky about 50 degrees long. And now from this diagram, you can see that we could rotate the Webb about the Earth-Sun line, this horizontal axis, and that won't spoil our shadow situation at all. And so now this arc becomes an annulus that covers about 35% of the sky. So at any instant in time, the Webb can point at 35% of the sky and still be in the shadow of its sun shield. Now, as the Earth orbits the sun, we're rotating about this axis, the vertical axis, and one can see that over the course of a year, this annulus will sweep over the whole sky every 6 months. So every 6 months, the Webb can observe any spot on the sky and still be in the shadow of its sun shield. So that's how we cooled it. Now, we didn't put the Webb exactly at the L2 point. We put it in a small orbit about the L2 point. Why did we do that? We did that to keep the Webb out of the Earth's shadow. We're generating electricity on the Webb with solar arrays. It takes about 2 kilowatts of power to run the Webb. And so we need to keep it out of the Earth's shadow for that reason. This little orbit about the L2 point is unstable in the direction of the Earth-Sun line. And so it has to be maintained by station-keeping thrusters. And the propellant for those thrusters is forecast to last about 20 years. Okay, let's talk a little bit about that sun shield. The JWST sun shield has an SPF of 1,000,000. So if you had this on the beach, you would be very well protected. It has 5 layers to give it that SPF of 1,000,000. Each layer is made of a heat-resistant plastic-like material called Kapton that is thinner than a human hair. The sun shield is the size of a tennis court, about 70 by 40 feet. It has a special curved shape. And those of you who sew may realize that in order to make something curved out of flat cloth, it requires lots and lots of seams. And so each of the 5 layers is in fact a quilt of 50 pieces involving 7,000 inches of seaming, not done with needle and thread in this case, but rather with thermal spot welds. Each layer of the sun shield is coated with aluminum, except for the sun-facing layer, which is coated with silicon, so it really does look pink in reality. Here is an example of some testing that we did on the sun shield. Here, the sun shield is folded up inside a containment pallet, and these telescoping booms are pulling it out of the pallet. This is exactly what happens in space. These mylar tables are not there in space. They're there to provide gravity offloading in this test. You can see a person appearing in the middle here that gives you a sense of scale. You can see the quilting, and each layer has a cord that runs around its periphery. And so after these spreader bar assemblies separate the 5 layers, then that cord is tensioned to give each layer its special shape. You get the idea. All right, so the sun shield was the highest risk part of the mission. It involved 140 release mechanisms, every single one of which had to work perfectly or the mission would fail. 70 hinge assemblies, 8 motors, 400 meters of cabling running over as many pulleys. It was a very high risk aspect of the mission, but it all worked perfectly and continues to work perfectly today. All right, the other problem we had, the mirror being bigger than the rocket, to solve that problem, we adopted something called a segmented mirror architecture. So rather than build one 6.5-meter diameter mirror, we built 18 hexagonal segments that are mechanized to play together as if they were segments of one single mirror. And that allowed us to fold the telescope up like origami inside the fairing or nose cone of the rocket that we used. We used a French rocket called the Ariane 5. This is a 5-meter diameter fairing. This rocket is launched from Kourou Launch Center on the east coast in French Guiana, which is on the east coast of South America. The payload was 6.5 metric tons. And as I mentioned, there were lots of single points of failure that all worked perfectly. Now, the Webb telescope mirrors are not made of glass the way most telescope mirrors are. They're made of a metal called beryllium. Why did we use beryllium? Well, as the telescope slews around the sky, points to different objects in the sky in the shadow of its sun shield, there are small temperature gradients that will form in the mirror. And we didn't want those temperature gradients to spoil the shape of the mirror. So we had to find a material that had a low coefficient of thermal expansion at this enormously cold operating temperature of almost minus 230 degrees Celsius. And it turns out that beryllium has that property. Beryllium is a metal that starts out in a powder form, and then we compress it under tremendous heat and pressure to form a solid block of material. It's called a billet of material. And then after we go through all the trouble to do that, we machine almost all the beryllium away. This is the back side of a flight mirror, and this is the front side. And the front side, you can see lab equipment reflected in the mirror. But you can see that we're light weighting the mirror as much as possible. And the Webb mirrors have an areal density, a mass per unit area that's about 6 times lighter than the Hubble mirrors and represent the current state of art for lightweight telescope mirrors. Now, we have another problem, another big problem. How do we polish telescope mirrors? Well, we rub on them with gritty stuff until they get smooth and shiny enough. That's a room temperature operation. So if we're going to polish the mirrors at room temperature and then use them at minus 230 degrees Celsius, it means that we have to put in the wrong shape at room temperature to get the right shape at the operating temperature. This is done through the magic of computer modeling, but computer modeling is not perfect. And so we had to follow an iterative procedure in which we would polish the mirrors part way, put them into a specially instrumented space simulation chamber at Marshall Space Flight Center near Huntsville, Alabama. Then we would cool the mirrors down to their operating temperature, observe them with special optics test equipment to see how reality in the model are tracking to each other. Then we would make adjustments to the model and continue the polishing. And this process took a very long time. This is one of the reasons why it took so long to build the Webb telescope, but it was completely successful in the end. Shown here at the upper right is actual data on a typical flight mirror segment. Here you have the room temperature figure of the mirror. So these colors are denoting peaks and valleys in the surface of the mirror. And when we take that and just cool it down to the operating temperature, the whole thing flattens out to a nearly perfect mirror. And so we had to do this 18 times, and that was all done successfully. When we finally got the telescope optics built and assembled, and we got all the science instruments mounted to the telescope and the spacecraft put on the telescope, it was then too big to fly in any kind of cargo aircraft. And so we had to put the Webb onto a special roll-on, roll-off transport ship. And we shipped out of Seal Beach, California, just south of Los Angeles, and went through the Panama Canal over to the launch facility in French Guiana. This is the first time NASA has delivered a payload to a launch site by boat. And this all worked very, very well for us. All right, so here we are now in French Guiana. We're riding up an elevator alongside the Ariane 5 rocket. There are work platforms set up along the rocket at various points where people are getting the rocket ready to fly. We're going to go to the top, see where the Webb is being joined to the rocket itself. And this is the very last view of the Webb telescope on the Earth. Spacecraft is fully fueled at this point, so the technicians are wearing these special safety suits that protect them from the toxic fuel. And then the nose cone or fairing of the rocket is integrated over the Webb telescope. Then the rocket is moved out to the launch site on a crawler vehicle. It actually goes very slow. People will be walking alongside it. And then we got it out there, and then we launched it.
And we have engine start. And liftoff. Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
Okay, the launch was very successful. Right after launch, lots of deployments occur. First, you saw the solar array come out so that we could become power positive. We're operating on batteries up to this point. And then you saw the high gain antenna come out so that we could start communicating with the Webb. We followed something called a direct transfer trajectory to get from the Earth to the L2 point. We did not orbit the Earth even once. There were some course correction maneuvers that had to be made along that journey, and they were all smaller than expected, which is one reason why we have so much fuel on board to do the mission. This was all very successful. This shows how the telescope unfolded. You see the secondary mirror come down here. There are some ancillary radiators and other deployments that occur. And here you see the wings of the primary mirror unfold, much like a round drop leaf kitchen table. All right, now when we first get on orbit, we don't have one telescope. We have 18 hexagonal segments, so we have 18 separate telescopes. Each segment is mechanized in 7 degrees of freedom, the 6 that you're familiar with, plus radius of curvature. So when we first pointed this telescope at a star, we get 18 separate images of that star. Then we would move each segment to figure out which image went with which segment. And then we would adjust all the segments to put those 18 images on top of each other. Superpose all those images on top of each other. And then we use special interferometric optics in one of our science instruments to make each segment coplanar to its neighbors to within a small fraction of the wavelength of light being observed. And that process led to a nearly perfect image. And we're exceeding our image quality requirements by about a factor or 2. All right, it is literally true that the Webb telescope is giving humanity its very first high-definition view of the infrared universe. And this chart shows that. This is our first, on the left, you see our first infrared, one of our first infrared telescopes, dating back to 2009. This is observing a particular field. All 3 of these images are the same field in the Large Magellanic Cloud. And this WISE telescope had a diameter of 40 centimeters. Later on, we developed the Spitzer telescope, which had a diameter of 85 centimeters. So you can see the Spitzer image is clearer than the WISE image. But then we've launched the Webb telescope, whose diameter is 6.5 meters. And now you see the remarkable clarity that we have never, ever had before in the infrared. And a lot of the science capability from the Webb telescope comes from its ability to see fine detail. Here's an example of what galaxies look like in the infrared with that fine detail. We've never seen stuff like this before, and the science resulting from it is quite remarkable. With the Webb, we've been able to do spectroscopy, like we talked about on the exoplanets, with galaxies dating back to when the universe was less than a billion years old. And you can see that we're able to measure the chemical composition of very distant galaxies to create very high quality spectra. We're able to see the shapes of galaxies in the very early universe. And this is turning out to be somewhat of a surprise because we're seeing morphologies or shapes that are very symmetric. That was not expected this early in the universe. We're also able to see black holes occurring in the universe when the universe was only a few 100 million years old. And we're able to see that these black holes are much bigger than thought possible. It may be the case that the Webb is observing a type of black hole that was theoretically predicted to occur before we launched the mission. in which black holes can form by direct collapse of clouds in the very primordial universe. So we'll have to stay tuned to see how this turns out. But this is an example where the Webb telescope has worked with an X-ray telescope called Chandra to prove that this object is in fact a black hole. The Webb is seeing how the universe was reionized. The universe started out as a hot plasma, and as it expanded and cooled, the atoms and the electrons and protons in that plasma could get together to form atoms so that the gas was neutral and then light could escape. But then something happened in the subsequent evolution of the universe to reionize the interstellar space. And the Webb is seeing what is causing that reionization. The Webb is seeing that dwarf galaxies in the very early universe are the ionizing out bubbles of in the neutral gas surrounding them, and these bubbles get progressively bigger and begin to coalesce to form the reionized universe. When a star like our sun runs out of fuel, it produces something called a planetary nebula, and that's what's shown here. This has nothing to do with planets. The sun will throw off its atmosphere to produce a giant nebula like this. And this is Webb's image in the near and mid-infrared of a nebula called the Ring Nebula. And we're seeing this level of detail that we have never seen before in the infrared. You see all these radial streaming structure. You can see all kinds of hydrocarbon and dust emission here. And so it's very, very exciting what the Webb is showing us. When a star that's more massive than our sun dies, it dies in a very energetic explosion called a supernova, which leaves behind a remnant called a supernova remnant, like this one. This one is Cassiopeia A. This is a supernova that occurred 340 years ago. So people saw this then and wrote about it. These supernova remnants are of great scientific interest because all the heavy elements in the periodic table are synthesized or forged in these supernova explosions. So when you hear the statement, "We are star stuff," it's literally true. The calcium in our bones, the iron in our blood, the gold and silver in our jewelry were made in supernova explosions near the Earth. Here is another example of a very recent supernova, supernova 1987A, in a companion galaxy of ours called the Large Magellanic Cloud. And the Webb has been able to see the progenitor star of that supernova for the first time. All right, so how does the universe work? How did we get here? Where are we going? And is there life out there? The Webb mission enables the next step in humanity's quest for answers to these questions, and you can join the quest. The people that build systems like the Webb come from all walks of life, in all backgrounds, and you can be one of them. There's a quote that I like to read. "The book of nature lies continuously open before our eyes, but it cannot be understood without first learning to understand the language and characters in which it is written. It is written in mathematical language, and its characters are geometrical figures." That's as true today as it was 400 years ago when Galileo said it. So to work in this field, the field of aerospace, go to college, study whatever you love. But if that happens to include science, engineering, or math, then you should consider this field as a completely practical thing to aim at in terms of what you'd like to do as a profession. If you'd like to know what it's like, You can apply for either a NASA or an ESA internship. And if you'd like to get involved in research projects like this, but you don't want to become a scientist, you can do that too. NASA has a program called Citizen Science, which you can learn about at this website. And despite the name of the program, one does not need to be a US citizen to become a citizen science and join a space research team. All right, what's coming up next? In October of this year, the Europa Clipper will be launched. Europa is a moon of Jupiter, and it's one of those ocean worlds. And Europa Clipper will be working on understanding Europa and the possibility for life on Europa. Next year in 2025, the SphereX mission will be launched, which is a mission that will take infrared spectra of every single object in the entire sky. And then in 2027, the Roman Space Telescope will be launched. This is a telescope similar in size to the Hubble that will study dark energy. Dark energy is a mysterious phenomena that is causing the expansion of the universe to accelerate, to increase in its rate of expansion. Then in 2028, a really cool mission called Dragonfly, which will be a helicopter that will explore the surface of Titan, the biggest moon of Saturn. And then in 2040, the Habitable Worlds Observer will be hopefully launched. And that is the true UV optical successor to the Hubble Space Telescope. So the Habitable Worlds Observer will be about the same size as JWST, but it'll operate in the UV optical spectrum. All right, so that's what I have to tell you today. I'll be happy to answer questions. First, along say let me.
Yeah, so thank you. Your presentation's been extremely interesting. I know for whole headers, I've really enjoyed it. I have like one question that is correlated to what you've just mentioned about the concept of the dark energy, especially connected to the expansion of the universe. So if we're saying that the universe is expanding always, does this mean that the universe is finite, so, or is the universe infinite?
Well, the universe is infinite, but will it expand forever and become just an empty, cold, dark place? Or will it expand and stop? Or will it expand, stop, turn around, and start to contract? The answer to those three, we don't really know yet. But in the late 1980s, it was discovered that the rate of expansion is actually increasing due to something called dark energy that no one understands yet. And that is what the Roman telescope is geared toward working on.
And another thing is why the telescope has been sent by Guyana, not by, for example, not from Florida or from Houston, so from the NASA usually like the NASA centers, the mainly one US, instead why it has been sent in South America?
Well, the Webb telescope mission is too big a project for NASA to do by itself. And so it was a collaboration between NASA, the European Space Agency, and the Canadian Space Agency. And one of Europe's contributions to the program was the rocket and the Ariane 5 rocket. And Europe's launch facility for the Ariane 5 is in French Guiana.
Okay, perfect. So I thought that it was something like linked about like the direction or physics, or like how to stay in the telescope in that specific position, so on, the rotating of art or something correlated to that. Are there any other questions? Mm.
All right, well, I hope everyone has a pleasant Sunday evening.
Yes, thank
And,
you.
and thank you for tuning in.
Thank you very much. It has been wonderful.
Okay.
Thank you so much for this presentation. It was absolutely wonderful. I learned so much.
All right. Well, thank you all, and enjoy your evening.
Bye. Thank you.
Thank
Have
you.
a
Bye-bye.
great day.